Hello, everyone. Good morning. How are y'all? Doing pretty good. Well, I was like, you're having a very good morning, Green. Someone had an extra cup of coffee today. All right. So if you didn't see, I posted the quiz. It'll be available today and tomorrow by request. It'll be the same deal as last time, 30 minutes. You get one attempt, but it'll be open till the end of Saturday. And it's going to cover 16, 3, 4, and 5. It will not cover Green's theorem. So, yeah. And let me make sure you can actually see the quiz this time. All right, I need to add an upload. Let me do that. Yes, good. I will do that after this. Upload. Okay, cool. All righty. So let's look at Stokes' theorem. This is probably the most complicated stuff in the entire course. Very involved. And yeah, so we got to make sure we understand how to do stuff step by step. Let's get started. So this is the second of our big integration theorems. And it is basically Green's theorem in R3. Pretty much exactly what it is. So remember Green's theorem, we're in R2. In R2, we had a region D, and we looked at the positively oriented boundary curve, or it could be multiple curves as we saw at the end. But D is a two-dimensional region, and we look at the boundary curve of this guy and orient that according to the rule. Basically, you walk along the boundary curve so that D is always on your left. So for Stokes' theorem, now we're going to be in R3. And instead of a two-dimensional region in R2, we have a two-dimensional region in R3, a surface. So suppose this is our surface S. So we need to give our surface an orientation. So we define at each point positive unit normals, and they're going to point on one side or the other of the surface. So suppose this is our guy here. So we're going to look at the boundary of this surface. So the boundary is going to be the edge of the surface. You can think of the boundary as a region where you can cross from one side of the surface over to the other. And we'll have to orient the boundary of our surface. We'll see how to in just a sec. Yes. But yeah. So the setting is essentially, it's the same as Green's, except now we have a surface in R3 instead of a planar region in R2. We orient our surface and then we look at the boundary accordingly. Okay, so there are sort of different things. Surfaces in R3 are obviously going to be more complicated than two-dimensional regions in R2. And so there are a few different things that can happen. Right, so you can have one boundary curve like this guy. You could have multiple boundary curves. You could have two or more. So we could have, say, a cylinder. Suppose we give it the outward pointing orientation, if this is our S. And then our boundary would consist of two pieces. The piece along the top, the curve along the top, and the curve along the bottom. So the boundary of S would be two curves here, or you could have three curves or four curves. You can have as many curves as you like, but we can also have surfaces with no boundary, namely closed surfaces. So suppose we have an entire sphere. So if you're a closed surface, you have no boundary. So our boundaries in R3 of our surfaces, so they can consist of one curve, like this first guy here, or two curves or three curves or four curves, so on. But they could also consist of nothing. You could have a boundary which consists of nothing at all, right? Because there's no edge on, well, edge is maybe a bad way to think of it, but there's no way where you can cross from one side of the sphere over to the other, right? There's no boundary of the sphere. All right, let me give it an orientation just because. Okay. So let's look at how we orient our surfaces. And so S, the surface S is going to come with an orientation. There are two possibilities, right? You can have your normals pointing on one side, and you can have your normals pointing on the other side. The way we orient the boundary depends on how we orient the surface S, which choice of orientation. So this is slightly more complicated than for Green's theorem, because for Green's theorem, D has no orientation, right? All we have to do is say counterclockwise for the outer boundary, clockwise for the inner boundary, or just think of it as walking along the edge so that D is always on your left. For surfaces, oriented surfaces in R3, what you do is you think of standing along, let me draw a picture again here. So suppose this is our surface S. And we give it this orientation. So for each part of the boundary, for each curve, you think of standing along the boundary curve with your head pointing in the direction of the unit normal vector on S. So at each point, so imagine you're standing on the boundary. On the boundary, we're going to define a unit normal vector at that point. So put your head in that direction. So suppose we're standing like right here. Let me erase this guy. Suppose we're standing at this, wow, I didn't mean to do yellow there, my bad. At this point on the boundary here. So we're going to stand so that our head is pointing in the direction of the unit normal vector. So imagine that unit normal vector is like a stick figure. There's our beautiful stick figure, and our head is pointing in the direction of the unit normal vector. So we're going to walk along the boundary so that S is always on our left. Whoops. So S is oh my goodness, it's really bad today. I'm losing my mind. Okay. Okay, this is sometimes difficult to visualize, but let's do our best. So we're standing on the curve with our head pointing outward in this case. So if we're looking down, if you're looking down, do we want to go around counterclockwise or clockwise? So let's try and visualize this. What direction do we want to go so that S is always on our left? So looking down onto this, right. So we should be going clockwise. We should be going in this direction. Does everyone see that? This is kind of hard to visualize sometimes, but that is a rule. Imagine you're walking along this with your head pointing towards the unit normal vector for the surface. What direction do you need to walk so that S is always on your left? Well, if you're looking down, we would go around this way. If you're looking down, it would be clockwise. And then obviously, if you switch the orientation of S, you're going to switch the orientation of your boundary as well. And we do this for each curve on the boundary. This is maybe one of the more difficult things to do, but does everyone see what's going on here?
Wait, so are you always going clockwise was, or does it depend on the curve is what you're trying to say?
It depends on the orientation of S, right? So if I switch the orientation, if I now had the same surface, but I had inward pointing normals, we would stand in the same spot. But now our head would be pointing to the inside. And so if we wanted to walk along there with the surface always on our left, we would want to go in the opposite direction. So it depends on the orientation of your surface. It takes a bit of practice to visualize some of this, and some surfaces are easier than others, I will admit. There is kind of another rule you can use. And I find this to be easier when it's applicable. You can use a right-hand rule sometimes. Sometimes this works. For some surfaces, it doesn't really, but for stuff like this, it does. Like for a cylinder, it wouldn't work very well, but you could point your thumb in the direction of your unit normal vector for S. So you wouldn't be pointing it in the direction right near the point on the boundary. Just like pick a point, like I guess in the middle. So for this one up here, say point your thumb in the direction of your right hand, obviously, of the unit normal vector for S. Say it's pointing in general downwards. So then you curl your fingers inward in the direction you're going. This really kind of only works if you have like one boundary surface. If you have more, it's not going to work so well. It's usually going to be the case that you're just going to have like one boundary surface. But curl fingers. Let me say, fingers curl inwards. In the direction of the orientation of the boundary.
So in this example, would your body still be facing, like when you say point your head in the direction of, and your body would still be facing be along the curve, but you would turn your head either outward or inward?
So for the first rule I gave, yeah. you would yeah, the normal would tell you which direction your head's pointing, either towards one side of the surface or towards the other. For the right-hand rule thing, this really only works if you have like one boundary curve, but like your unit normal is going to, in general, point like in the negative z direction or positive z direction or something like that. But like it's in general, this is sort of the downward pointing normal for this surface. So point my thumb in the downward direction. My fingers are going to curl inwards. If I look down on it, my fingers are curling inwards in the clockwise direction. Does everyone see that? So like point your thumb down, my fingers are curling in clockwise, and that tells me the orientation of this boundary curve. So this is useful if you have one boundary curve. It kind of breaks if you don't. But if we do it for the other guy down here, if we give it the opposite orientation, my normals are in general pointing upward. And so I curl my fingers inward. I'm going around Now, if I'm looking down counterclockwise, does everyone see how that matches up here? This might be an easier way to do this, less mentally taxing, if you understand how it works. But I want to emphasize this kind of doesn't work if your surface has more than one boundary curve. You got to use the first rule. Okay. I don't want to spend too long in this, but I want to make sure everyone understands this because this is very important, how we orient the boundary. Okay, everyone's great with the these two rules. Okay, so if we use this first rule, you stand, imagine you're a vector, right? You're standing on the boundary curve. Your head is the tip of the vector. So you're going to be oriented so that you're standing in the same way as the normal vector, right? So if I'm standing on the curve, the boundary curve right here, my head is going to be pointing in the direction of the unit normal vector. So either your head is going to be facing one side or the other. And that determines how you're standing on there. And then you want to walk along the edge so that S is always on your left. So like one thing you could do is you could draw your little stick figure and then just draw the left side. Let's do that down here. In fact, let's do like a cylinder here. Okay, suppose we have a cylinder and we have inward pointing normals. Now we have two boundary curves, we need to orient them both. So let's draw our little stick figure. Okay, so we're standing sort of inside the cylinder. If we're doing that, our left is going to be on this side. Wait. No. Sorry. So we can obviously turn around, but the side, okay. Here, we want to draw your hands on the side facing the surface. Okay, so we want that to be our left. So our left is facing the surface. If that's our left, we're going around, whoops, in this direction. Does that sort of make sense? And then we'll do the same for the bottom. So we're along the bottom. That's us. We're sort of pointing our head inwards. And then the side that's facing the surface is that. So we want that to be our left. And so we're going around in this direction. This may not work for you, but this kind of makes it easier for me to visualize. And so that's the orientation on that. We'll get some practice on this. But I gotta move on. Okay. All right. So here is Stokes' theorem. So in this setting, S is an oriented surface with the boundary of S oriented as we just mentioned. We'll say it's given the positive orientation in that case. That's how we positively orient the boundary. So the boundary of S is oriented according to the rules we just said. And capital F is going to be some vector field that satisfies some technical criteria that's always satisfied in here, so don't worry too much about that. Then, this is basically exactly like Green's theorem. So we have the integral over the boundary curve of the vector field F. So this is just like Green's so far, integral over the boundary curve. That's equal to, but now instead of integrating over a region in R2, doing a double integral over R2, we're integrating over a surface and we're integrating, instead of F, we're integrating curl of F. So this is exactly like Green's theorem. Remember, because in Green's theorem, we integrated the thing that we check to see if the vector field is conservative. We do the same here. We're integrating the curl of F, which remember, the curl of F is 0 if our vector field is conservative. And so then if we integrate over the boundary, each piece is a closed curve. If you integrate a conservative vector field over a closed curve, you get 0. And the same is here. Same is true here. But if your vector field is not conservative, then you're not going to get 0. But still, we're integrating the thing we check to see that our vector field is conservative. Also, if S is a closed surface, then the boundary is the same theorem holds, but the boundary is empty. It doesn't exist, right? So then if you're integrating over nothing, you get 0. And that's the case. So if S is a closed surface, then the right-hand side, the integral over S of curl of F, doesn't matter what F is. If you integrate the curl of F over a closed surface, you get 0. Right? Just think of integrating, wow. Think of integrating F over nothing, right? You get 0. Right, so if you're integrating the curl of F over a sphere, you always get 0. Only true if you're integrating the curl of a vector field. Not everything is a curl of a vector field, right? Because we've integrated several things over spheres and not gotten 0. But if what you're integrating is a curl of a vector field, you always get 0 over any closed surface. That's a good thing to remember. That's a nice conceptual question that could be asked. What if the vector field is non-conservative? Doesn't matter. You could take any vector field. If you take the curl of it and you integrate it over a closed surface, you're going to get 0. So that's a bit of confusion. Not every vector field I give you. So if I just said instead the integral over a closed surface of a vector field, any old vector field, not necessarily going to be 0. But if it's the curl of a vector field, it's going to be 0. So some vector fields are curls of other vector fields. Most are not. I hope that's not too confusing. Usually it's going to be written literally as the integral of the curl of a vector field. And that is always going to be 0 over a closed surface, Sorry, I hope that did not cause too much confusion. Okay, so literally Green's theorem, except now instead of integrating over doing a double integral over a two-dimensional region, we're doing a surface integral over this oriented surface, and we're integrating the thing we check to see if the vector field is conservative. We're integrating curl of f.
So if it's an open surface and it's conservative, then that's the only way it equals 0. But if it's a closed surface, it doesn't matter if it's conservative.
It could possibly happen to equal 0, but if it's conservative, then it's definitely going to equal 0.
And that's only for an open surface. But if it's a closed surface, no matter what, the curl of the vector is going to be 0.
So the curl is not 0 on a closed surface, but if you integrate the curl of f, you're going to get 0.
Okay.
Yeah. Just think of it. You don't even need to memorize that separately. Just think of this as applying Stokes' theorem. So if I integrate the curl of f over a closed surface, that's the same as integrating f over the boundary, but the boundary doesn't exist. So you're basically integrating a vector field over nothing, right? Which is 0. Maybe that's a little easier to grasp. Okay. So let's verify Stokes' theorem. Once again, so we did an example of this for Green's, where we did both the both the integrals. In practice, this is not what you're going to do. You're going to be given one integral, and you're going to use Stokes to turn it into the other type. But we're going to do both here, just to show. So we're going to verify Stokes for the vector field f, which is going to be negative y, 2x, x plus c. And S is going to be the hemisphere x squared plus y squared plus z squared equals 1. Z greater than or equal to 0. So the upper hemisphere. With outward pointing normals. So a lot of stuff to do here. Okay. So first thing, it's very good for these to draw a sketch. Really helps to visualize and to get the orientation right. So we have our sphere of radius 1. We're looking at the top half, and we're going to orient this so that, so if we had the entire sphere, so if you have a closed surface, there are two orientations. There's the outward pointing one and the inward pointing one. This one, if we had the entire surface, the normals would be pointing outward. And we're only taking half that, but we keep the orientation on this guy. So this is our hemisphere, our extremely beautiful hemisphere here. And we're doing the top half. So the boundary is going to be the circle in the XY plane. Okay, so we can use the right-hand rule here. So if we're looking down on this guy, because I said this bit, because I said z is greater than or equal to 0. So you can use either the right-hand rule to orient the boundary curve or the point your head in the direction. I find the right-hand rule easier if there's one boundary curve here, which there is. So if we're looking down, are we going around this boundary curve counterclockwise or clockwise? Right, we're going, if we use the right-hand rule, our thumb's pointing up, and we're going around, looking down counterclockwise in this direction. Does everyone see that? Okay, we're going to have to roll. So Stokes says we're going to do both of these integrals, but let's write it down. The integral over the boundary curve of the vector field f is equal to the integral over the surface S of the curl of f. Okay, so let's do both these guys. So first, let's do S. Let's do the right-hand side of this. Okay, so we're doing an integral of a surface. First step we always need to do for a surface integral, no matter what we're integrating, is parameterize a surface. Really, you need to have enough experience with these in an exam situation that you can just pull out a parameterization of a sphere like that. Otherwise, these problems are going to take a really long time. So remember, we're just going to use spherical coordinates, but we're going to let rho equal 1 because we're x squared plus y squared plus z squared equals 1. In spherical, the equation of that is rho equals 1. So we're going to get 1 times sine phi, whoops, cos theta, 1 times sine phi sine theta, and 1 times cos phi. And theta is going to go from 0 to pi over 2, because we're the upper hemisphere. So we have stuff on the positive z-axis. That's phi equals 0, sorry, phi. And we're opening up until the xy plane, which is phi equals pi over 2. And then theta is going to go from 0 to 2 pi, because we're going all the way around the z-axis. So that's our parameterization of our surface. So we also need, we know ds is equal to that n of phi theta, the normal vector. So remember, it's either g sub phi cross g sub theta or negative of that. And remember, we know the rule. For the outward pointing normal, if we're a sphere, we know that is just the radius squared, whatever the radius is of the sphere, in this case it's 1, times sine phi, times the radial unit vector, which is just, you look at the parameterization and you divide by the radius. Well, the radial unit vector is just our parameterization itself now because our radius is 1. So when we plug this in, the radius is 1. We just get sine phi times the radial unit vector, sine phi cos theta, sine phi sine theta. Right, just the parameterization divided by the radius, cos phi. And then you can bring the sine phi in, but I like to leave it out. So that's our outward pointing normal vector. Okay, in the interest of time, I'm gonna move on. Okay, so we're integrating the curl of f. I gotta move on, Nick. I'll go back at the end if that's okay. Sorry. So remember the curl. My apologies. Why are you coming down, dude? Go up. There we go. Thank you. So the curl is just del cross f. And so let's write that down. So del is, remember, ddx, ddy, ddz. And we said f was negative y, 2x, x plus c. And when we do this, so we get I ddy times x plus c, which is 0, ddz minus ddz times 2x. We get 0. And then doing the same, so we get 0 minus 1. And then we get 2 minus negative 1. So our normal is just 0, negative 1, 3. No, not our normal, sorry, the curl of our vector field. Which is nice. It's a very simple curl. Very simple thing to integrate. It's just a constant, which is nice. Okay, so we are plugging in our parameterization. So phi goes from 0 to pi over 2. Theta goes from 0 to 2 pi. Our curl of f is just 0, negative 1, 3. And since it's a constant, there's no x, y, or z to replace. So it's still 0, negative 1, 3. And then ds is our n of phi theta, which we said was sine phi times the radial unit vector. So sine squared phi cos theta sine squared phi sine theta, sine phi cos phi, and then our dAs just, come on, don't do this, d phi d theta, and so taking the dot product, we get negative sine squared phi sine theta, whoops, plus 3 sine phi cos phi, and we should be able to evaluate this by now. So for the sine squared phi, we would need to use the sine squared phi as 1/2 1 minus cos 2 phi. But I'll just give you the answer. We should get 3 pi for the answer here. Yes. But the important bit is that we can set this up. And then once we have it written down, we should be able to evaluate the double integral. Okay. All right, I'm going to move on really quickly and just set up the other integral. And then I can go back if you'll need. Okay, so let's do the other integral and show that we get 3 pi. So let's do the boundary. So redrawing this guy, if we're looking down, we're going around counterclockwise along the boundary curve. And so let's parameterize our boundary curve. Okay. Okay, so our boundary curve is just in the XY plane. It's that unit circle. So we can think of it as being in the XY plane. But remember, we're in R3, so we need to say what X, Y, and Z are. So first of all, if we're in the XY plane, what can we say about X, Y, or Z? No matter what our curve is. Right, so we know the XY plane is Z equals 0. So Z is always going to be 0. That is correct. So we know Z is 0. And let's see what happens with X and Y. So we have the unit circle. And we're going around counterclockwise if you're looking down on it. And so how do we parameterize the unit circle going around counterclockwise? X is going to be what? Cos t, right? So we let X be cos t, Y is sine t. And we let t go from 0 to 2 pi. Does everyone see that this parameterizes our boundary curve? The orientation was important. If we gave S the opposite orientation, then we'd be going around clockwise. And instead of cos t sine t, there are different ways to do it, but you could just switch the two. You could say x is sine t, y is cos t. That's going to go around clockwise. Or you can change the sign on one of them. You could say x is negative cos t, y is sine t, or x is cos t, y is negative sine t. All of those will switch the orientation. But x cos t, y sine t goes around counterclockwise. Okay, that's our boundary curve. And we're going to be integrating a vector field, so we need r prime of t. So r prime of t is going to be negative sine t cos t 0. And so let's do our integral. So the integral of our vector field over the boundary. So we plug in our parameterization. So t goes from 0 to 2 pi. Our vector field f, remember, was negative y, 2x, x plus z. And when we replace x, y, and z with their parameterizations, negative y becomes negative sine t, 2x becomes 2 cos t, and x plus z becomes cos t plus 0. Let me just write that plus 0, that's fine. And we're dotting that with r prime of t dt, because that's what dr is. So we're dotting that with negative sine t cos t 0 dt. Okay, so taking the dot product, we get integral 0 to 2 pi. Negative sine t times negative sine t is sine squared t. 2 cos t times cos t is plus 2 cos squared t, and then plus 0. You could simplify this if you like. Sine squared plus cos squared is 1. And then we're left with another cos squared. And when we integrate this, we see we also get 3 pi. Which is what we wanted. Okay, yes. I can go back now if you like. But all of this is very involved. For a Stokes theorem question, you need to know Stokes theorem. You need to look at the problem and know you need to apply Stokes theorem. So you're either going for the double integral of curl, or to the line integral, or from a line integral, which is the boundary of some surface, to the surface integral of the curl. And you need to know how to do either the line integral along the boundary or the surface integral along the surface. Many steps, and you need to make sure you understand each one. Why is the orientation important for the integral with curl? Because the curl of a vector field is a vector field. And when you integrate a vector field on a surface, the orientation matters, right? If you change the orientation of a surface and you integrate a vector field, you're changing the sign of your integral. Yeah, it's because the curl of a vector field is another vector field. And integrating a vector field orientation matters, whether it's a line integral or a surface integral. Okay, anything else? Alrighty, so do Sunday at midnight? I think so. The homework's due Sunday. I think Saturday's already. I think Saturday is probably the latest I could do it, but I guess email me, and I guess it depends on your circumstances. But I'd prefer to leave it Friday and Saturday. But send me an email, and we can talk about it. Okay. Anyways, have a great day. We'll finish this up on Monday, or have a great rest of your weekend. And yeah, so homework due Sunday, quiz open today and tomorrow. And yeah, I will see y'all on Monday.